start? Okay. So, yeah, so we'll continue what we started last Friday. So, I'll start with a very brief recap. And I think notes should be ready. Rajit has kindly agreed to scribe, and he should be emailing the scribe sometime soon. So, we talked about some gamma, which is set of relations over some domain D. And then we had this problem CSP of gamma, which was basically you have some n variables and then you stipulate that some collection of subsets of variables are constrained by some relation in gamma. Okay, so and we saw different gammas lead to different problems. So this is the whole class of problems, and then we also had an important notion of polymorphism of gamma, which is basically operations that preserve membership in all relations in gamma. Okay, so for every, so this is also can be defined as intersection of polymorphism of R in gamma. Okay, and then just to very quickly recap this, what is polymorphism of R? You can write down some tuples in R, x1 to x, let's say, so this is in R, y1 through yk is in R, z1 through zk is in R. And let's say you have a ternary operation of arity 3, then you have f of x1, y1, z1, dot f of xk, yk, zk is also in R. So if this happens for every triple, that implies f is a polymorphism for R. Okay, and the set of all polymorphisms is called denoted pol of R, and it has some very nice properties. First of all, you can always just the projection functions are always polymorphisms because you can just copy one of these rows. Again, you want to think of polymorphisms as if I write down a bunch of rows in the relation, applying the polymorphism column wise will give you a new tuple in the relation. Okay, so that's and I guess it's some sort of closure property in this, and then I want to just throw out this sort of vague buzzword as well. You can think of this as some sort of analog of discrete convexity. So it's a discrete function under which these things inside R are closed. And if you have some, and really the overarching principle is that if you have rich families of polymorphisms, there is somehow enough mathematical structure that that's going to lead to algorithms. And if you sort of lack polymorphisms, interesting polymorphisms, then you're going to be hard. Okay, that's the general polymorphic principle, which is completely well established in CSPs, and somehow our motivation has been to sort of use the CSPs as a launch pad to try to extend this principle to more general settings. Okay, so that's the current road, but I'll probably talk mostly still about CSPs today as well, and then maybe go to some extensions next week onwards. And then we just had some examples of this. For example, if you have, just to say, so if you have linear equations, so you could have f of x, y, z is x minus y plus z is a polymorphism for linear equations. Okay, so poly for linear equations. Okay, so all this is recap, and towards the end of, and why is this the correct thing to do? And we stated the dichotomy theorem also, which is that basically a CSP gamma is in P if Paul gamma has non-trivial functions. Okay, so non-trivial, roughly think of it as non-projections. It's a little bit more nuanced for non-trivial operations, let's say. Else, it is NP complete. Okay, and this is the algebraic dichotomy, which was finally, it was conjectured. The dichotomy conjecture itself was late 90s. The algebraic version, which pinpointed the boundary between tractable and intractable as a property of the polymorphisms, was formulated in mid 2004, 2005, and then 12 years later, 2007, it was established. Okay, so as of now, so last year, this is now a theorem. Okay, so all that is good. Yes. Yeah. So, okay. So, one very nice thing about polymorphisms is that they have very rich, there are some nice properties by their definition. So, one thing we said is that, so projections are always polymorphisms. Projections, or in CS, the CSP folks call it projections. You know, we like to call it dictators, or always polymorphisms. And then the other property is that closed under arbitrary compositions. Okay, and the best way to think about it is that you can take any tree you want, any tree structure, label the leaves with arbitrary indeterminates, allowing repetitions x, y, z, x, x, y, whatever, right? So, x, y, z, x, x, y, z, a, p, something like this. Label the internal nodes with arbitrary polymorphisms of the correct arity, of course, based on the number of children it has. You will get a new composed function that will also be a polymorphism. So, for example, if for 2 sat, because majority of 3 is a polymorphism, you can build a recursive majority of 3. So, you can say majority of 3 of majority of 3, majority of 3, majority of 3. So, this is an operation of arity 9. It is called recursive majority of depth 2, and then you can go to arbitrary depth. And I remember mentioning this exercise that using this and some clever restrictions, you can prove that majority of arbitrary odd arity are also polymorphisms. I mean, of course, that you can verify that for 2 sat trivially, but it's also a property of polymorphisms. So, if a polymorphism clones, so these are things, anything with these 2 properties are things called clones in the universal algebra language. So, if majority of 3 belongs to polymorphism R, automatically majority of 5, 7, 9, everything must belong to this. Okay. So, it has a lot of rich functions. So, in some sense, once you have one interesting function, you can compose it with itself many times, and you can get more interesting functions. And this has been a very important tool in CSPs. And one of the challenges we face in extending it to things like promise CSPs and so on is that this composition breaks down. So, when we come to that, I will explain that. And somehow, initially it seemed that because of that maybe this algebraic theory does not apply, but basically it just means that a richer, more complex theory needs to be developed, but I think algebra still will play a role. Okay, this kind of thing. And then these sorts of objects are studied in this field called universal algebra. So, even before the connection to CSPs, people studied functions under compositions for a long time, and clones, and classified all Boolean clones and so on. So, there was a lot of work. So, once the connection was made, people were very quick to take all that work from universal algebra and apply it. Any other questions from last time? Okay. So, okay. So today what I want to do is that I want to maybe prove something. So far it has been sort of overview. I'll prove this thing called the Galois connection. So you have some set of relations lambda. I'll say that lambda PP defines, and I'm going to define what PP defines is in a second, but let me just state this thing. Or it can also be written as gamma belongs to the closure under lambda of PP define if and only if okay. And what is this PP define? It simply means that you can express any relation in gamma as a projection of some relations in lambda. So I'll just give an example. Suppose R is in gamma, so let's say its arity is 3. Just to give an example, R ABC. Gamma PP defines means that, so this will imply that CSP, okay, so let's write it this way. So CSP gamma can be reduced to CSP lambda, and that means this is an easier problem. So there is an inversion, okay, and that's maybe hinted at by the term Galois connection. Right? So, yeah, this is always a terminological issue, but this.
Conjunctions of projection.
Yeah, conjunction of projection. So I'll just define what PP define means. So it means that any relation in R, let's say it's a ternary relation, should be written as there exists some other auxiliary variables Z, and then some conjunction of arbitrary things in lambda. Okay, so P1 of A Z1 and P2 of A B Z2 and so on and so forth.
Projection of conjunction.
Projection of conjunction. So it's an existentially quantified statement. So, you can express a relation in gamma, every relation in gamma as a conjunction of relations in lambda, including auxiliary variables. So, it is just how you do normal gadget reductions. Okay, we took algorithm, the basic algorithms course, you are asked to reduce 4 sat to 3 sat. I mean, this is sort of what you do. Okay, that is all. I mean, you introduce some auxiliary variables, these are constraints you are allowed. So, you can express this in terms of this. Okay, and that clearly implies it is a very restricted form of thing. So, if I give you an arbitrary CSP gamma instance, I can take each clause and replace it by a collection of clauses in this, including some other variables. Okay, this is equal. This is actually equal as a relation over all ABC. So yeah, so basically this relation is equal to this quantified form, where ABC are free variables. So you can take an arbitrary relation, express it as relations this. Therefore, you can take a, suppose you have an instance phi here, you can reduce it to an instance psi in the original variables plus some extra variables.
Psi may have polynomially many
More variables. You can use new variables for each constraint, but it's a polynomial time, in fact, log space reduction. Okay, so I can put log space. So this implies this. Okay, but the nice thing is that for this class of reductions, polymorphisms exactly captures this. But even if you don't care about this particular thing, if you just take this fact, this so this is implied by poly. So if you have more polymorphisms, you reduce to the other problem. Okay. And why is that good? That means that if two sets have the same polymorphisms, they are interreducible to each other. So polymorphisms capture from the perspective of complexity up to polynomial time or even log space reductions, polymorphisms are the correct two. So you can't have two things with the same polymorphisms but differing complexity. Okay, and this is really gives the whole study a firm grounding. Okay, so let's try and prove this. So this is a theorem. Any questions about this? PP define, or PP define simply means that you can express relations in gamma as conjunction of relations in lambda followed by a projection which throws out the auxiliary variables.
Why would the other way inclusion not be true?
So
Because gamma is defined in terms of lambda, right?
yes. So you will see. So when we do the proof, you will see that because any polymorphism of this will automatically be a polymorphism of this, but may not be the other way. And it has to be the case, right? For example, you can reduce 2 sat to 3 sat, but 2 sat has more polymorphisms, so it really only goes one way. Yeah. Okay, so let's do there are two directions now. So the first, the easy direction. So now proof. Any questions? Okay, so now let's do the proof, two directions. Obviously, we'll start with the easy direction. So if you PP define, then any polymorphism of lambda is also a polymorphism of gamma. Okay, and that's easy to see because take an arbitrary relation in gamma. So let me just write it. It's easy by inspection, but let's do the inspection now. Take an arbitrary. So you have R A B C. So you might have some tuples A1, B1, C1. Suppose all of these are true. Let's just do an example. Suppose you have an arity 3 function which is in polymorphism of lambda, and you want to prove it's also a polymorphism of R for any relation R in gamma. Well, you just wrote this as there exists Z, some conjunction of Pi, so and of Pi of something, some A, Z, some projection, right? And that's true for each of these things. So now, because F is a polymorphism of, so what you can do is that if this is true, there is some setting of these auxiliary variables here. There is some setting of auxiliary variables, let's say Z1, Z2, there exists Z3, and so on. And now you explicitly use that auxiliary variables. Now you have a giant formula of and things. There is no quantification. Okay, and now you just apply the polymorphism on the PIs. You know that the new thing you will get will be a polymorphism, will be in PI. Okay, so the point is when you apply the polymorphism here, ABC will obviously go to F of A1, A2, A3, right? And this will go to F of B1, B2, B3. So these are the three variables. So that's what you will have here. So you want to prove that this, sorry, I should have written it here. You want to prove that this belongs to R. That's equivalent to finding some setting of auxiliary variables. And what will that setting be? Take the auxiliary variable z1 for the first guy, z2 for the second, and z3 for this. These are all vectors, but then apply f component wise to these. That will give you a new set of auxiliary variables, and that will satisfy all these guys, and therefore, okay, it's really just follows from definition. Okay, if you want, you can just write as R, let's say is P1 of A, B, Z, and P2 of B, C, W. Let's say it's a simple example like this. So there exists ZW like this.
The polymorphism of lambda allows you to combine Z1,
Yeah.
Z2, Z3
into a new auxiliary variable suitable for exactly f of A1, A2, A3, B1, B2, B3. Okay, does everyone sort of buy this? Again, if you didn't follow it online, don't worry, it's really just follows from the definition. Just because I didn't write it very clearly here, but you just write a formula like this and just exactly as Arvind said, apply the polymorphism to the auxiliary variables to give you a new auxiliary variable. Okay, that's one direction. So, but the more interesting direction, the more direction we sort of want is that if you do have more polymorphisms, then you do reduce. Okay, and so we have to prove that. Okay, this will take a little proof, but okay, no, maybe it's worth doing once. So I might need a cheat sheet for this proof. All right, so let's try and do this proof. It's not hard. It's just really just, it's very syntactic, follows the definition of polymorphisms and stuff like that. Let's see. Okay, so this we have to do this, but note that that's the direction we want. So once we do that direction, so we know that the moment some polymorphism, suppose polymorphism of some lambda is just the projections, then you know that say 1 in 3 sat will reduce to this. Okay, so note that a corollary of that other direction, corollary of this direction is that, you know, if polymorphism of lambda equals just the projections, which is sort of the minimum it could be, that implies CSP or let's say this is 1 in 3 sat reduces to CSP lambda, and therefore it's NP complete. Okay, and note that you can check that it's a simple exercise to check that polymorphism of this relation 1 in 3 sat is exactly projections. So once your projections, once you have nothing more than projections, you can take an NP-hard problem and reduce it to it. So this is sort of the easier direction of the dichotomy. So getting hardness out of lack of polymorphisms is quite easy. Okay, I mean, so this is when you have exactly projections. Sometimes you might have projections and some more functions still be hard, like non-Boolean domains, but it's still a much easier task than the algorithmic. Okay, so this is the corollary. So just to keep in mind, this gives you more or less automatically the hardness side. Okay, so so let's see. Okay, so now here is a little lemma we'll prove. So or basically I want to reduce, I want to PP define gamma for in terms of lambda. I will do it in terms of using an intermediate thing. Okay, so I'll use an intermediate CSP which somehow corresponds to polymorphisms and use it to then define gamma. So let's define, so let's make a definition. So let's define SL to be all these functions, and actually this whole thing I'll do generally. It doesn't, you know, you can think Boolean if you want, but everything is completely abstract nonsense at some level. So just it works.
L is the arity.
L is an arity, yeah. So this is just a relation. Okay, so SL note is a subset of D to the D to the L. So it's a relation which is very big, but basically it contains all those tuples which as functions are polymorphisms. Okay, so it takes, so this is a single relation which consists of those functions. So it's a relation sitting inside this. Okay, and you can think of this naturally as a function from D to the L to L.
All the Ellery polymorphisms.
All the Ellery polymorphisms. Okay. And you might wonder what the role of L is. It's going to come later, but so this will be what I'm going to say first will be true generically for all L. Okay, so the following is true. So for all L, gamma PP defines, and note that this notion of PP definition is transitive. So what I'll prove is I'll prove gamma PP defines SL, and then for every L, and then for some large enough L, SL will PP define gamma. Okay, maybe I should have really used A and B. So this lambda and gamma mentally is, so maybe you can do that in the notes. I don't know. So I myself don't. I mean, somehow A, B, I can have some sense of which is reducing to what. Here I have to look at the board each time to get it right. But so let's first do this. So gamma PP defines SL. Okay, and this really, this is the kind of thing which is cannot explain. I think you just have to.
You want to write poly gamma there. F in poly in definition of SL.
No, here it is lambda. Yeah, everything is lambda. Yeah.
You want to say lambda PP defines, but SL is a subset of lambda. SL is
No. But lambda is in a different space. It's more or less you're right. So if you feel this is obvious, it sort of is. Once you will see it, it's. But is
thinking of these polymorphisms as relations,
right?
And these relations you are saying are PP defined by lambda.
Yeah. So later, which will be in like 5 minutes. So for some large L, we'll prove that SL PP defines. And this will be more or less trivial gamma, and then the composition will finish the proof. Okay. Yes. 2 sat, 3 sat is good to keep in mind. Yeah. Though I don't know if the proof becomes any sort of easier in this thing, but yeah. Right. Yeah. Exactly. Yeah. So yeah, maybe A, B would have been better, but yeah. So somehow A, B. So these people use like in the survey, these slides of Andre Krokin I sent from CCC, they use A and B. So then it's if you can, but somehow just A and B seems confusing. They like to have embellish the symbols somehow, but okay, it's also standard. These Greek, capital Greek things. Okay, so let's see if we can fit it in this column. Okay, and really the proof of this is pretty much follows from definition, right? So basically what do you need to say? You need to say that you have to somehow capture the property that F is a polymorphism using relations in R. But that's kind of obvious, right? What in some sense you should expect that's obvious, because what is the polymorphism thing? It says that if you write down some tuples which are in the relation and then you apply F column wise, you should get something in the relation. So let's just let's just try to write down all those constraints. Okay, so let's just do that. So basically let's write down some tuples x1, x2 to xl. Okay, so I don't know why I'm using.
So right now you've taken one such F in SL and you want to.
No, not one such F. I have to give some conditions which will characterize Fs. Okay, so right now what I'm doing is I'm going to take arbitrary L tuple in where each one of them is in R for all R in lambda. And if you really think, if it bothers you, just think of lambda as containing of just one relation. Nothing really changes if it's a collection of relations. You just do it for every relation. But for each one of these relations, you take all of these things and you just literally write down the property that F must be a polymorphism. So namely, if you apply F column wise, so let's call the columns y1 to yt. Well, t is the additive of R. Okay, and then what is the property? We want that F of y1, F of yt is in R. And that's it. That's going to be the PP definition. So you have this. So you will impose these particular conditions. So you have this big string of length d to the L. You want to say when is it in SL? It's in SL when it's a polymorphism. That means you're basically going to go to some of these t tuples corresponding to these yi's for every one of these and say, oh, these things must belong to R. Then some other things, those things must belong to R and so on. So, the property of being a polymorphism to R is just a conjunction of some various carefully chosen subsets of these things belonging to R. So, in fact, in this case it is just a conjunction, there is not even a projection going on.
So this huge tuple is in SL?
Yeah, if and only for all these things, these corresponding columns for all matrices where the rows are in R, the columns, the locations corresponding to the columns in this big string must be in R.
And you run over all the
And you just run over all of these tuples. Each such matrix will give you some collection of this, and then people convinced? I mean, it really just follows from the definition. So, the fact that you are a polymorphism for R is naturally definable by a conjunction of things belonging to R. Okay, and this is like a long code kind of gadget which we use in approximation. Somehow it was discovered in this community also for an independent reason. Okay, so it's somehow okay. So, this is true for every R, and therefore you just write down this collection of constraints for every R, and this you get this. Yeah, yeah. Okay. So, you want to, so you have, you're testing for a function belonging to SL. Okay, so I want to give a criteria. I want to express. So, let's think of that thing as a long string of length d to the L. So I am saying that if this long string is a polymorphism, if and only if the following is true for every t tuple which you can get here. Note that these things are of arity L. So, the columns here are of size L. So, for every t tuple of relations, of things in the relation, read off those columns, right. Sorry, for every L tuple of things in the relation, read off those columns. Those will correspond to some locations. So, let us say these 4, right, L is 4 here, sorry, T is 4 here, that should be in R. Then you go to another matrix, say that that part should be in R. And if once you exhaust this for all matrices, you have expressed the condition that you are a polymorphism.
Essentially, by long code, you mean each such function you think of as one huge tuple.
Huge tuple, yeah. So, you just want to characterize this thing belonging to SL as a conjunction of various t tuples belonging to R. That's all. Yes. Yes, exactly. We didn't even need auxiliary variables, and this actually comes up, and this is also the reason why this polymorphic principle is also useful for exponential time, fast running, studying the exponent of the best run time. And I'm going to comment on that either today or next week. So, there is this concept of partial polymorphisms, which exactly captures this. And if two sets have the same partial polymorphisms, or if one has more partial polymorphism, then it will run in faster c to the n time, where c is smaller than the other one. So, using this, you can identify, for example, the easiest NP complete problem, which has the best exponential runtime and so on. Okay, so yeah, this part does not use projections at all, and the second part is going to. And the second part is more or less just going to be, we are going to take this big relation and we are just going to project it into some subset of coordinates. But I want to make sure people understand this. It's not so important. I mean, it's at some level, as I said, it's some sort of abstract business. But it's nice way to also make sure that you understand what polymorphisms are.
Since we want polynomial time reducibility from gamma to lambda, when we mix you take the number of conjunctions here.
Yeah, so one thing, note that everything here is fixed. So, D is a fixed domain, L I think of as fixed. So, this is, yeah, it's horribly big, right, but it's exponential in L and all that, but it's still fixed, it's constant. Okay, so it's okay, so express these conditions. So, yeah, so I didn't write it down properly, hopefully his scribe can do it, and I think it's there in this Hubi-Chen survey, for example. Yeah. And you can even.
For this SLPP defines gamma, basically you want to say that all the relations are already sitting inside SL, no? Because projections are all there. And
yes, yeah.
That's all.
Yeah, that's more or less what one wants. Yeah, so I'm going to define that projection pretty much immediately. So, is this clear? So, I am now have this intermediate relation. Now, what I want to do is that I want to basically say SLPP defines gamma, okay, and that's going to be a very simple projection. So express. So this conjunction defines this. So now what do we do? So now we need to say that let P be in gamma. Now we do the second part. take an arbitrary predicate in gamma, and again you can basically pretend there is only one predicate because you will do this for every relation or predicate, and let's just write down this to be x1. I'm just using m, do not confuse with this, but m is going to become L basically. So let P be this.
Each xi
is a tuple in this relation. So this is all a subset of some d to the t. I think I use t, or it doesn't really matter. Okay, and this is okay. So we define like this, and now what we are going to really do is that let's just claim. So now the claim is this. If I take all, so let's just take the following thing. So again, I'll do the same thing. So I'll write xi's in as rows and read the columns, which is y1 through yt. And I'm simply going to project this SL or SM onto these things. So let's now just consider the set f of y1, f of yt. Okay, so actually, so that was t was used there. So let's use k here just to say it's something different, because the arity of thing p may be different than this. Okay, so this is what k, suppose k thinks f in Sm. So let me define this particular relation. Okay, so now the claim is that this is in fact p. P is nothing but the projection of the polymorphisms of lambda at these points. So this is where the basically I introduce the auxiliary variable, and this is where, since you're projecting, the rest become auxiliary variables. But somehow conceptually it's nice to go through this intermediate gadget. So you test for a polymorphism, and then you simply say P can be obtained as the value of this polymorphism at these points. And that will imply, of course, that SLPP defines this. Okay. Okay, so we'll prove this, and that will finish the proof. Any questions? Okay, so one thing you might is that, okay, in PP definition, I think some people look puzzled, and it might be a valid point, is that you might actually think, how do you say this? So let me just expand that a little bit, because you do need equality constraints as well. So you want to express some z's in P as something being in Sm. Okay, so this I'll prove. This is very easy, and this is just a little claim. There won't be any confusion in this. But the grander picture, why does this imply that P can be PP defined by this? So this means that there is some big function f, right, such that f is in Sm, right, and you're also going to say that f of y1 equals z1, and f of y, did I use k, is zk. So this part you will agree, right? So this is just the definition once I prove that P equals this, and this is a valid PP definition, because basically you're, in all these PP definitions you're allowed equality constraints as well, I should have said, because if two variables are equal, you can collapse them. So when I say PP, when something PP defines another thing, I can use relations in that, but I can also use equality relations for free. Okay. I mean, and of course you can syntactically eliminate this, right? So because you can, whenever f was appealing to this, you could actually use z1. So there is a way to eliminate the equality constraints. Okay, so this is the PP definition. So now let's just try to prove this.
This is just a reformulation of that statement.
Yes, this is just a reformulation of that statement. I'm just writing it more sort of blatantly, so it's apparent why it's a PP definition. Okay, so now let's prove this fact, that P is equal to this. So let's call this right hand side to be some delta. So part 1, P is contained in delta. Both parts are simple, but part 1 is maybe even easier. Anyone see why this is the case? That anything in P must be in the right hand side. So what are all the things in P? These are x1 through xn. So I want to get each one of these rows as f of the columns for some f. So what f's should I use? So use the projections, right? So if you use the m projections, so use f equals pi 1, pi 2 to pi n. And then simply use the fact that pi j of y1 to yk is simply equal to xj. Okay, so every one of these. And you might be puzzled, so far I never used the hypothesis that polymorphism of lambda is contained in polymorphism of gamma. Okay, so I have to use it somewhere. Right. So far everything I said was generic, right? So this PP defining this long code is generic, and this part is also true. Now the part 2 is delta is subset. Okay, and so what do I need for that? So I know that f is an Emery polymorphism of lambda, and therefore it is also an Emery polymorphism of gamma. And therefore whatever I have here, whatever y1 through yk may be, right? So these rows, so sorry, whatever this f may be, these rows definitely belong to P. In fact, they are all of P. So whatever, if f is in polymorphism of gamma, then applying f column wise, this new thing should also be in P. So I can never go outside P. Okay, true, because f is in poly lambda, which is contained in poly gamma. Therefore, any f you put here is a polymorphism of P, of everything in gamma, in particular of P, and then this is true. Yeah, I mean, this is not a difficult proof, it's just notationally cumbersome, I think. It's just.
Definition, you had this there exists Z1, there exists Z2. Now you are actually putting a function, you're kind of smuggling in a function.
Yeah, the function is just because it's really just a tuple, right? So you can, for example, here I wrote it in function form, but I could have written as f sub y1, f sub yk. I mean, just because my index things are strings, it's natural to think of it as functions, that's all. But this is really the, say if I wanted to do it in one shot, I could have just said this is the PP definition, that's it. And then you just use the fact that this part itself can be written as a bunch of conjunctions of things in lambda and Newton. So I just broke the proof into this midpoint for conceptual clarity. Okay, but this is the overall PP definition, and this part is a PP definition from lambda. Equalities are for free. So yeah. Okay, so that's actually a very important, I mean, it's not a very difficult theorem, but it's obviously conceptually very important. It says polymorphisms are the correct tool, and as I said, this really Galois correspondence extends to many other settings as well. Okay. All right, so
Does it automatically, is it only polynomial time reductions or even log space reductions?
these are all log space reductions, yeah. Because this PP definition is log space
Maybe
reduction.
even AC0 reductions. Because only conjunctions and projection.
Yeah,
Tasking.
I don't know. I think I'll defer to your judgment on that. Yeah. So, but all I can say is that some of these things, it's not so easy to do it in log space. I think, for example, so Josh and I managed to basically extend it to promise CSPs, which I'll talk about later. But really, the extension is pretty much just follow through this proof. But then something happens, and it's not so clear how to do that in log space. So I think we just claimed polynomial time. I mean, I'm pretty sure it can be done. It's just that we weren't sure, so we didn't claim it. Okay, so we finished that. So let's see. So now, okay, so maybe what I'll do is there are two directions. I can talk a little bit more about CSPs, or I can talk about extensions. So maybe I'll still continue to talk a little bit about CSPs. But then I'll comment at some point, if not today, maybe towards the end of today's lecture, I'll give a teaser on variants of polymorphisms which capture other things. So there are appropriate variants which capture optimization, approximation, and also the exponent of the fastest exponential runtime. So all these things are already in place for CSPs. Okay. And then there are also things beyond CSPs like promised CSPs as well. But now let's continue maybe doing a little bit of, just to give this idea that polymorphic principle in the thing, rich polymorphisms imply algorithms. So no non-trivial polymorphisms so this is roughly the principle we are talking about. And by this Galois connection, we more or less already saw this other part. So if you don't have any non-trivial polymorphisms, then you can just take some NP complete problem and reduce it. Okay, so for Boolean case, it's pretty clear, but for non-Boolean, there are suitable extensions you can do it as well. Okay. So in particular, if there's nothing but projections, the Galois correspondence gives us a reduction, log space reduction from say 1 in 3 SAT. You just have to verify that 1 in 3 SAT has no non-trivial polymorphism, which you can, just do by some simple combinatorics. Okay, so and that will give you this hardness. So the algorithmic part is a difficult thing, but I will do some very sort of simple teaser cases where I'll assume some amazingly nice polymorphisms, and then I'll give you algorithms. Okay, and really in some sense these will all be inspired by. So we already saw for Horn SAT and of anything was a polymorphism. For 2 SAT majority of anything is a polymorphism. So let's try to just abstract away a little bit from the relations, exact Horn SAT and other things, and just say what property of these polymorphisms can give you algorithms. Okay, and all this is like very simple classic stuff, but it might give you a little bit of flavor of why polymorphisms can help algorithms. Admittedly, these are very, very easy cases, and we'll maybe work our way to slightly harder cases later. Okay, so which one do I want to do first? Okay, so maybe I'll. Okay, so let's start with this following things, and this is all this is in that polymorphisms and how to use them survey. So let's talk about this most. So I'm going to make some strong assumptions on what polymorphisms I have and give algorithms. So this next part is just make some bold assumption, which of course is not unreasonable because some interesting problems have that property, and then give algorithms. Suppose you have totally symmetric polymorphism of all large enough arities. Implies efficient algorithm. In particular, the width 1 algorithm, which I am going to describe. And I should also tell you what totally symmetric means. Totally symmetric simply means that if I have f of x1 through x, suppose it's an arity L thing, this is simply only depends only on the set of values which occur. So you can give me any L tuple with multiples, in any order, with any repetitions and all that. Nothing matters, only the set matters. If only the multi-set matters, then you get a symmetric function. So only the set matters, on the set. An example, of course, is AND. Okay, and that's why this is basically a generalization of a very simple standard algorithm for Horn SAT. Okay, so that is totally symmetric thing. So the function only depends on the set of values it sees. And what is a width 1 algorithm? So width 1 algorithm is, I guess I could just write down this algorithm, but basically what you do is, I'll say the algorithm in words, and if needed, I'll write it down. So and all this works for any domain. Okay, but if you want, you can think of Horn SAT. So what do you do for Horn SAT? You say that initially you say that for each variable you can have either 0 or 1. Okay, then what you do is you can then say if some variable is set forced to 0, you force it to 0, and then that might force some other variable to 0, and so on and so forth. And then you keep doing this, till you make progress. And then at the end, if somebody becomes empty, then it's not satisfiable, of course. And the one thing to prove is that if you do terminate and you haven't found a contradiction, you are satisfied. Okay, So, that part, that is Horn-Sat algorithm. In general, the width 1 algorithm will be something similar. So, again it is written down in this survey. So, I will just quickly write it down. So, you will say that, so if, so, so Px is, so I will use the same notation as that. So, this is the set of allowed values for variable x. So, you start by allowing it the full domain, and then so you say that for all constraint which you are in the instance, what you do is that you know that each one of these should be in this domain. So, intersect the relation with that, and then for I equals 1 through k, now you can project, now you can update this Pxi to be Pxi intersect the projection onto xi of r prime, okay, and then replace r by r prime, and then keep looping till you make any change at all.
Till it doesn't change.
Till it doesn't change, yeah. Because once it doesn't change, it's, yeah. Okay, this is not meant to be a super efficient algorithm. I guess it will be polynomial time, but you know, it's not the fastest algorithm. So, this is called a width 1 algorithm because you basically deduce some you only look at single variable at a time, and you say that the space of constraints meet to be into a smaller set, you make that update, and then you keep inferring, but you never really look at pairs of variables, for example. So, width 1 means that it's really the simplest possible algorithm. Okay. For something like 2SAT, for example, you will have to do width 2. So, you will have to look at pairs of variables, and then say, because it will have constraints.
All the PXs are non-empty.
Yeah. Yeah. So, yeah, I didn't, this is really sloppily written, but in the end, if Pxi is not equal to empty for all I xi, implies there exists satisfying assignment. So, that is the only thing you need to prove. Obviously, if some Pxi is empty, there is no satisfying assignment because every inference you make is sound, right. So, you just have to do the other part. Okay, so how do you prove this? So, prove, so this is the fact proof, and that is where we are going to use the polymorphism. Okay. And the nice thing here is that note that the algorithm does not refer to the polymorphism at all, but the proof of correctness will refer to the polymorphism. And then next I will give an example which will correspond more to 2SAT, where I will use the polymorphism in the algorithm itself. But either way, there is this nice connection on why you have an efficient algorithm. So, how are we going to do this? So, we are going to take, so what I am going to do is that I am going to fill a, so I have to use the polymorphism somehow. So, I am going to fill a large number of, okay, sorry, I should tell, okay. So, proof is that let n be large enough, or maybe I will use L be large enough, and then I will simply take this totally symmetric polymorphism, and then I will say sigma of x equals T of Px. So, the assignment I give to variable x will be, or if I use xi, I guess xi is sigma of Px. So, I see the set of values I get, I simply apply T to such a thing. Oh, so T is arity L polymorphism. Okay. So, I mean it's sometimes called a term. T is a totally symmetric term, yeah, of arity L. So, it will exist for any large enough L. So, I'll tell you how large L needs to be in a second, but this is going to be my assignment. So, basically I haven't emptied out any variable. So, I have some set, I simply apply my polymorphism to that set, that will give me a value in D, and I am going to claim that that is going to work. I guess you could actually now say that you are using the polymorphism also in some sense. I mean, if you want to, for example, do the search version and find an assignment, this will be a way to get the satisfying.
T needs an L tuple.
T needs an L tuple. So, this is a set, just repeat things arbitrarily. It is a totally symmetric thing. So, whatever you do, it will only depend on this set. So, just repeat say one of the elements in Pxi enough times to expand it out to an L tuple. And L will be much larger than D. So, this will never, you always have. case, I think people look confused, but this is, I think I didn't say.
T of Pxi means that this
Yeah.
is a set of elements that occurs in the.
So T somehow you can, F can be written as just a function on set, it's well defined. So then I just do this. Okay, so okay, and I just have to prove this works. So why will this work? Suppose you have a relation R constraining x1 through xk in the constraint. So I need to prove that sigma x1 to sigma xk will satisfy R. And how am I going to do this? I'm going to write down a big matrix where the tuples are all going to belong to R. So there will be L of these so that I can apply the polymorphism. And what I will basically do is that so I will write down tuples such that everything, so each one of these will belong to R, and in column I will exhaust Pxi. All the elements in Pxi will occur. So why can I do this? And I can clearly do this if L is more than the domain size times the arity of the relation. So why is that? Because for each xi and each value in Pxi, the fact that this value is alpha in Pxi, the fact that alpha still sits inside Pxi means there is some relation which had that particular value, some row here which had that particular value and this after. So I can do that for every value in this, and then I move to the next variable and do these things.
Isn't it possible that R in some position doesn't have a particular value at all?
So if it didn't have a particular value, then you should have eliminated it. So okay, so I think there is one subtle point here, which I think is probably what is bothering you, is that, see, note that I am updating my R by R prime. So it's not like this is the same R, but
what you get at the end.
At the end, yeah. So this, I should really put R prime here, and you might now say, well, you know, R prime is not my original, it may not be in the original gamma, but it doesn't matter. It's slightly, you know, important but subtle point. But the point is that this R prime still preserves the polymorphisms. You can check that anything which is a polymorphism of R will still be a polymorphism of this guy, because it's basically just doing some PP definition type thing. Okay. So you can write down for every value in Pxi, you can write down something in R prime which contains that value in that location. So as long as you have more rows than the number of domain things and the number of locations, you can fill up this matrix. And then by definition, when you apply T of Pxi, the new thing you get will be in R prime. And so you will satisfy R prime. And note that if you satisfy R prime, you definitely satisfy the original R, because that was just obtained by an intersection. This is really just the Horn-Sat algorithm explained a little bit more generally. See, in the usual Horn-Sat algorithm, what do? You force things to 0 or 1. The remaining variables, you set it all to 0. Okay, again, I can never get this 0 or 1 right, but for one of the variants, you set it to 0. Why is that? Because and is a polymorphism, and of 0, 1 is 0. So all the variables which are not set so far, basically there are no unary clauses, and every non-unary clause has a negated variable. So by setting everybody else to 0, you are in good shape. And in the polymorphic view, what is happening is that those remaining variables have Px equals 0, 1, the full domain, and you do and of that, you going to get 0. So it's exactly a case of this algorithm. Okay, so this is like very simple algorithm. But yeah, but you made a very strong assumption on what kind of polymorphisms you have. And I should also say that this characterizes with one algorithm. So if you want to say for which CSPs will this simple algorithm work, it will only work if you have a totally symmetric polymorphism. With one is basically this algorithm. So if this algorithm is sound for all instances of a CSP gamma, then that must have a totally symmetric polymorphism. So this characterizes with one working, yeah. And that survey has some references on why, I mean, I don't quite know how to prove the converse, but it points to some papers which do it. So this characterizes the power of with one algorithms. Okay. Okay, now any questions about that? So So that was totally symmetric polymorphisms. Now I'll weaken it slightly and still give you an algorithm, and then we'll maybe close with some general remarks. 1228. Okay. Okay, that was one. So now instead of totally symmetric, I'll just assume that you have a symmetric polymorphism of all big enough arities. That implies efficient algorithm. In fact, it implies that the basic LP. So I'll tell you what the basic LP is works. So you can write a very standard linear program for any CSP, and which will be a relaxation. So if you're satisfiable, the LP will be satisfiable, but it's a relaxation. Sometimes LP may be satisfiable and you may not be, but if you have a totally symmetric polymorph, if you have a symmetric polymorphism, the LP will exactly tell you when you're satisfiable. Okay, and an example of this will be 2-sat. Oh, not 2-sat. Sorry, sorry. Again, 1-sat. Again, and so for ON-sat, the LP will also work. Okay, and I'll tell you what the LP is. And is the poly ON-sat. Not quite 2-sat, because for 2-sat you only have majority of all odd arities, so it's not going to be quite as simple as this particular. Okay, so you need slightly more. Okay, so what is the basic LP? So you have some constraints. Again, remember that we wrote an instance of CSP this as this complicated, this Pij of x I1, no x. Oh. Something like this. So you have a conjunction of these classes. Each one of these belongs to gamma. Okay, so you have many of these. This is the way I wrote this. Okay, so if I messed up the notation, don't worry, you know the idea. So you have some variables for some tuples. For each tuple, you have some tuples which are constrained. Each constraint should be from your template gamma. So what will a natural LP be? And again, I'll do it for general domain. Okay, so suppose you have variables x1 through actually I'll do it a little bit. Yeah, so for each v in variable, suppose I have variables v and constraints c. Okay, some c. Okay, which are these collection of these PIJs. Whatever. So for each variable, I need to assign a value from D, from this domain D. So instead, I will say that it will be assigned a value. So I'll give you allow fractional values. So it will be allowed a value. There will be a vector xv. So actually, maybe I should refer to my notation so I don't mess up this part. Yeah, it's okay. We'll make it up. So it's not so bad. So I'll have a vector like this, where xvi is 0 for all I in D, and summation xvi I in D is 1. So basically, for each variable, instead of asking you for a value in D, I will ask you for a distribution of values in D. So these will be my LP variables at the variable side. Okay, now for each constraint C in the constraint set, okay, this will have some arity and so on. So now again here I will have, so I know that the values here must belong to this constraint. Okay. So what can I say? So once again, so here I am allowed d possible values, here I am allowed some number of values. So what I can do is that I can basically list all the things in C. So sigma 1, sigma 2 to sigma m. So these are all the things in this. Let me use predicates because that's what I've been using so far. So you take all the predicates, satisfying assignments of the predicates, and then I can ask, so what does it mean for it to be satisfiable? For each variable I can give one value in D, and I can also give one tuple for each constraint, and somehow the tuples must be consistent with the variables. That's another way I can think of the satisfaction problem. So for each 1 in 3 sat clause, you can tell me which of the 3 satisfying assignments makes you happy, and for each variable you can tell me which value 0 or 1 you give, and if you do this in a way which is consistent, then you have found a satisfying assignment. Yes, that view is often useful. So that's what you want to do here. Okay, so for all Pj, so you can have this basically some convex combination of, so you can have a convex combination on its satisfying assignments. Okay, so for each one of these constraints which you have there. So this is the variable part. This is the, for each constraint on each set of variables, you will say that you will have a convex combination on distributions. And now what will the LP say? It will say that for each variable and each constraint it participates in, its distribution matches the marginal of this distribution on that variable.
So what is the distribution for P?
Or actually, you know what, let me just write down, so sorry, what was the question? So it would be an arbitrary distribution.
Okay.
Yeah. So, or let me just write it down in really brutal notation with all the subscripts and so on. So write the natural LP will be the following. For all, suppose you have an instance like this, the way I originally wrote it. So for all j in J, what I will say is that oh, I see, there may be some confusion. It certainly works for the Boolean case. Now in the non-Boolean case, sorry, yeah, so so it's a little bit difficult to write down. So okay, so let me try to still explain it in this. So suppose you have a constraint like this on these variables. Suppose the arity is something k. So basically, I have some set of d tuples, some set of k tuples from D which satisfy this. For each one of them, I can assign a non-negative number such that their sum is 1. So that gives me a convex combination. That basically gives me a distribution on satisfying assignments. And on this side, I will have a distribution on the values to the variable, and I will say that these are consistent for every variable and every clause it participates.
So sigma 1, all the entries of sigma 1,
yeah,
you will put down these double index variables.
Yes.
And the sum should be 1.
Yeah, let's try to write it down for one constraint. So suppose V participates, suppose you have a constraint P of V for some variable and some other guys. Okay. So basically what you will then say is that XVI is going to be the summation of, let's use values Y for this predicate. So Y sup P of sigma for all sigma in P, and sigma 1 equals, maybe I won't use I here, let me use A, just sigma 1 is A. And then for all P, you have these variables saying summation yp sigma is 1, sigma is 1. So this gives you, basically you have a distribution on satisfying assignments to every constraint, and you have a distribution on values to every variable, and you simply say that the distribution of variable C's is consistent across all constraints it participates.
So the value you give to XVA is apportioned to all the tuples wherever it occurs.
No, or it's consistent. Another way to think about it, the marginals are consistent.
Okay.
So the whole difficulty in constraint satisfaction is that different constraints might want different satisfying assignments to make them happy, but the problem is you want to do it in a consistent way. And here I am relaxing you to be satisfied by some distribution on your satisfying assignments, subject to the fact that your marginal on any variable, if I have two constraints containing a variable, the marginal of the first constraint and the marginal of the second constraint are the same, and in particular they are all same equal to this particular the global universal distribution. And you can easily see that this is an LP, right? I have basically written down what the constraints are, not very precisely with all the indices and so on, but hopefully the idea is clear. Okay, for every constraint like this I have this, and then if V participates in this and then it occurs in the first location, the sigma 1 is simply because it is in the first location. Okay, and then if you have W here, you will also have X WB is equal to summation YP sigma, sigma is in P and sigma 2 is B. Okay. No, I am not. This LP is you can write for any CSP, and then what will the and you will just check this PLP feasible or not. I won't even have an objective function. So basically, I am asking: is there a distribution on satisfying assignments to each constraint, which are all consistent at at a single variable level? So I will just check this, and I can do this in polynomial time for any CSP.
So in the exercise, you have an integral solution. Clearly, that is the solution to the CSP.
Yeah.
You can choose the y's as 1 by the number of places, something.
See, but this may not in general work for all CSPs. I mean, so the LP may be satisfiable even though you are not at all satisfied. Okay. And why is that? For example, let's just say you can take any 2-sat instance. For each variable you can give the uniform distribution half-half, and for each constraint you can give the values 0, 1 and 1, 0. I mean, you will put probability half on the truth satisfying assignment 0, 1, probability half on the satisfying assignment 1, 0, and these constraints are all, every marginal is uniform. But of course, not every 2-sat instance is satisfied. So even for 2-sat, this thing will not work. And note that 0, 1, 1, 0 are both satisfying assignments of 2-sat. But this is yeah, in fact, not even 2-sat. If you just think of checking if something is bipartite, even. This, according to the LP, every graph is bipartite. So even checking bipartiteness, which will not do like this. Yeah, I'm sorry I didn't write it down too crisply, but I think the notation will just be a mess. You just should have this idea that for each constraint you have a distribution, for each variable you have a distribution, they are consistent. And that's something you can easily express for any CSP. And now we just have to prove that if you have a totally symmetric, if you just have a symmetric polymorphism, this will work. So for Hornsat, for example, this will work. This the LP will solve it. So the local algorithm works for Hornsat, the LP works for Hornsat, and so on. These things don't work for 2-sat. Yet somehow Hornsat is, in the complexity sense, harder than 2-sat because you have NL completeness versus P completeness. But sometimes simplicity of the algorithm doesn't correspond to the complexity class. Okay, so now. Okay, so let's see why this is algorithm mostly clear. I mean, somebody can ask a question; it will help. Yeah.
If the original CSP was only discrete, we've gone to an LP where you relax the assignments very fast. So how does the feasibility of the LP now implies about
The original CSP. That's right. That's what we have to prove. So clearly. Okay, one thing I should say is that this is a relaxation. So why is that? If you are a satisfiable instance, then the LP will surely be feasible because you simply give the all your distributions will be point distributions. For each variable, give the corresponding value. For each satisfying each predicate or relation, put all the mass on the way it is satisfied. and of course this is consistent because you were satisfying assignment. So this is a relaxation. So a satisfiable instance, the LP will be satisfiable. But if the LP is satisfiable, the instance may not be satisfiable, and I gave you an example. So you take any graph, the LP you can express the fact that the graph is bipartite or not, and the LP will always think that any graph is bipartite because it will give a uniform distribution for each vertex. For each edge, it will put uniform distribution on 0, 1 and 1, 0, and the marginals are match. So okay, so that part is simply not true in most cases. But if you have a symmetric polymorphism of all begin of arities, then you can take an LP solution and round it to this other solution. Okay, and I am going to tell you how to do that. Okay, so what will the rounding be? Hopefully I won't mess this up. Let's see. So the rounding is simply going to be, so take an LP solution. So now, so what are we trying to prove? So LP satisfiable plus arbitrarily large, not arbitrarily large, plus symmetric poly of all arity, or large arities, implies CSP instance is also satisfied. Okay, this is what we need to prove, and I'll actually, and the proof will be basically algorithmic as well. But this is, if you just want the decision version, is the LP is the instance satisfiable or not? This already gives you this. Check if the LP is satisfiable. If so, output the instance is satisfiable. Okay, how are we going to do this? And the proof is going to be sort of have a high level similar structure to what we did before. We're going to somehow use the polymorphism, to round. Probably many of you have seen this. You take LP solutions and round it to an integral solution, to round LP solution to a satisfying assignment. Okay, that's going to be the idea. Okay, so how are we going to do this? Take the LP solution. Okay, and everything. So the LP solution will be rational. So you can assume that, so assume all values are of the form something by n, alpha I by n, okay, some star by n. So take the least common denominator of all the fractions which occur in your LP and so on. So basically assume that it's basically some number by n. All these numbers are actually at most 1, so it will be some number between 0 and n divided some integer by n. Okay. So you just assume this, and then what we are going to do is the following. Suppose you have a variable v here. So we are going to, so we have this frequency vector. Let's just take some example d to be 4, right? So it's going to have some frequency vector 0.1, 0.2, 0.3, 0.4. Hopefully they add up to 1. Okay. So this is like a frequency vector for that. So now basically I will round it up to n times 0.1. So basically I can now have these, let me define some frequency count. So let me use some new variable for that, some c count, cvi, to be n times xvi, which is now going to be an integer, natural number. So this is an integer because I have assumed that all the entries have denominator by n. So now essentially I have frequency counts for how much I think the variable I should get value. Let me use a consistently for this one. And now my value sigma x is simply going to be f. So this is a symmetric polymorphism of arity n. So obviously I can make n big enough. So I'll have a symmetric polymorphism of this. And now I'll take a symmetric polymorphism and then I'll give it some values d1 to dn, so dx1 to dxn, which is just any sequence where a occurs exactly CVA times. So note that summation CVA over all a in d is exactly n. So I'm just defining the rounding now, and it makes sense because I just convert these probability distribution into frequency counts. I just make up any tuple where the frequency of the different symbols matches that frequency count. The order does not matter because it is a symmetric polymorphism. Okay, that is the key thing, that is why this whole thing. So, you might wonder, oh, am I doing it in a consistent order with respect to another variable? It simply does not matter. Okay, you just take any tuple like this, f will be the same. So, where A occurs CVA times among the di's, among d1 to d. Okay, so everyone with me. So, in this particular case, suppose this was the frequency vector, you have n over 10, 2n by 10, 3n by 10, 4n by 10. So, you just take any tuple of length n where the symbol 1 occurs n 1/10 of the time, symbol 2 occurs 2.2 of the time and so on, apply f, that polymorphism, to that tuple, and that will give you a new element in the domain, and that is going to be my assignment to variable v, xv, variable v. No, so xv I used for the vector, so v is the variable. Yeah, my notation is all over the place. But really this, yeah, the notation just makes heavy weather of something very simple. For each variable, you have a distribution on possible values, convert that distribution into a frequency count by just clearing denominators, and then apply the polymorphism to a tuple which matches that frequency count, and that is your value, that is your rounding algorithm. Okay, that's, so I have given you the rounding algorithm, we have to just prove it works.
So capital N will be large numbers. So
Capital N will be some huge number maybe, yeah.
you can't efficiently do the round.
Oh, I see. So, you are saying that n might have, yeah, the bit complexity of n will be fine, that is right. So, that is why this is not necessarily an efficient rounding algorithm.
But the decision thing,
The decision thing is fine, yeah. But probably you can use the fact that there is no reason to, actually it may not even be, yeah, one has to be slightly careful, but yeah, there may not be any need to use any denominators more than some constant size, because everything is constant size. But yeah, so even in unary n may be fine. I'm not sure. So it's a good thing to think about. Yeah, but actually there are certain things for which we know how to do decision, but we don't know how to do search, and that's precisely this reason, because we use some large enough arity in the argument, and if that's too large, your rounding algorithm is not efficient. Okay, so yeah, as for now, let's just take this as a decision algorithm. So the Hornsat thing, it was fine, the algorithm was efficient, but here the algorithm, unless you argue n is small, may not be efficient. Okay, so now let's try and prove that that this is a correct algorithm. Okay, so let's again do that by example. Suppose you have a constraint on three variables u, v, w. Suppose you have some constraint p, u, v, w. I mean, it's very generic, so I just use 3 for. So suppose you want to prove that this is satisfied by this particular thing. So what do you know? So you know that there is some. So you know that for all. So you know that there is a distribution on satisfying assignments in P. Okay. So once again, you can clear by multiplying the distribution by n. You get a frequency count of different satisfying assignments for this. So you basically going to get some counts C alpha in P. Okay, so these are numbers. Okay, and now C alpha, and the summation of C alpha is equal to n. Scale up by the distribution on satisfying assignments of P to get this. I mean, do exactly what we did for variables, now for this constraint. So you have these counts. Okay, so now the claim is that you can, when you write down these counts, so now you just write down alpha C alpha times. So alpha 1 will be written C alpha 1 times. So alphas are all the satisfying assignments. I somehow use sigma for this, so okay, maybe I should have used sigma. Okay, so let's actually do that. So let's say this, the assignment is psi. So, I will continue with sigma. So, this is sigma 1 is written C alpha, sigma 1 C sigma 1 times, sigma 2 C sigma 2 times, and so on and so forth. Then we write C sigma m, which C sigma m times, where P is sigma 1 through sigma m. Okay, and some of these may be 0, some count may be 0, but this is general. And now comes the key point. If I look at a particular, and note that these are all here, I have taken this example of 3 things, but everything is generic. But suppose so this has basically 3 columns. This is just for illustration, I use 3. You can now ask what is the frequency count in the first column of the different elements of the domain D. So that must match the frequency count of U, right? So the distribution on assignments to P, the marginal matched the distribution on U. So that means that here all I did is scale it up. So I just converted distributions into numbers which add up to n. So the frequency count here, so the frequency vector matches CV, CU. So therefore, when I apply f here to this frequency vector, it is the same thing as what I did here. So this value, so I claim that f of this frequency vector has to be equal to psi of u. And the same for the second and the third column. And therefore, psi u, psi v, psi w must satisfy, which is my rounded values, must satisfy P. Because f is because they match f applied to these columns, and f, remember, is a polymorphism, and I wrote down a bunch of satisfying assignments, maybe with repetitions, it's allowed, and applied f. And that's the proof. Right, so that shows that this rounding algorithm is a correct round. So just write down the basic LP, which says test for satisfiability in the language of distributions. And if you have a symmetric polymorphism of big enough arity, then you're in good shape. But it's important that it's for all large enough arities. If you have symmetric polymorphism, for example, of only odd arities, which say 2SAT has, this won't work. Because you need the arity to match exactly n, and you may not be able to, the denominator might have to be even. Right? So it has to be exactly n. So you need polymorphisms of all large enough arities. As I said, for 2SAT or even like bipartiteness, this algorithm doesn't work. Okay, but something like this will work. So next time maybe I'll describe an algorithm using majority polymorphism, which will work basically by rounding. So, but I'll do that for Boolean case. You will just write the LP and say if you're more than half, you go to 1, if you're less than half, you go to 0. Okay, that sort of LP will work. That sort of rounding will work. All right. So, okay, I should probably stop. But just as some teasers, so I'll just talk about polymorphism beyond CSP decision. So far we have just talked about the problem of given a CSP instance, is this satisfiable or not. So we can talk about various things called max CSP. So I can give you a instance and ask, okay, maybe it's not satisfiable, but tell me what is the largest number of constraints you can satisfy, the optimization version. So next time I'll start with some brief remarks about this, and then you can sort of talk about approximate CSP, where you can say, okay, maybe this problem, most of the time it's NP hard. So you can say, okay, maybe you can't do that, but how well can you approximate? So you can say approximate max CSP. And then we can also talk about, okay, maybe CSPs are NP hard to decide, but fast exponential algorithms. Decision CSP. And then lastly, which is kind of current focus of us and few others is extension to promise CSP, which can also be viewed as some sort of approximation, but we'll come to that. And the point is that all of these have a corresponding notion of polymorphisms closely related to what we sought, but sort of some variant of these polymorphisms which capture their complexity. But the theory gets more complex, particularly for promise CSP. There is no conjectured criteria on the boundary between the tractable and NP. Okay, but the notion, we know the correct notion to look at. Just the notion seems pretty hard to tame or get a handle on yet. Okay, so that's probably a good time to stop and take questions if you have. Questions? You can also email me if something was not clear, or email Rajit, and we can try to address that in the scribes.
Break this further into, let's say, things which are in log space
Mm-hmm,
and things which are harder in log space. I mean, can the tractability be?
Yes, there is. I'm not very conversant on this, but if you look at this survey, polymorphisms and how to use them, they have conjectures on what things are in NL, what things are in L, and all that. So you go further beyond this structure. Basically, there is sufficiently strong enough structure of polymorphisms, symmetries, and they say that will correspond to these various classes. And some of those are, I think, still open. Like there is a conjecture for NL in that survey, and maybe even log space. So yeah, so they have looked at it, and there are.
This polymorphism machinery still is used.
It still is used. Yeah, I think the point is that anything which includes log space by the Galois correspondence, it captures the thing. Now the question is that do you know what that criteria is? The polymorphisms are a fine enough object to capture the complexity of anything above log space because of the Galois correspondence and the fact that that reduction is log space. And there are conjectures on what that nice property is, but that may not have always been established. And there are also connections to these things like data log and those sorts of inferences. So this, yeah, logical connections to logic, specific inference forms and so on. Yeah, I think what has been nice is, yeah, they have good understanding of when the fact that certain class of algorithms work is often exactly captured by polymorphisms. For example, I said this width 1 is captured by exactly having totally symmetric polymorphism. Now we can ask when is some small width captured, like width 2 and so on. So they have these collapse theorems. Basically, they know that width 2 algorithms more or less capture any constant width. And that constant width is also corresponds to the case when there are polymorphisms of all with some very minimal symmetry polymorphisms, like this thing called WNU, which I mentioned last time. If you have WNU polymorphism of all arity 3 and beyond, then you are bounded with. And that's if and only if. So they have these nice characterizations, and it's also equivalent to when you cannot express linear equations. So suppose if you can PP define linear equations, then that means that you cannot be solved by any of these local algorithms, because somehow Gaussian elimination is a very non-local procedure. So you are solvable by these like bounded with algorithms if and only if you don't PP define linear equations over any field, and in the polymorphic language that is if and only if.
This one is not a bounded width algorithm.
This one is not.
LP.
Yeah, one by LP. Yeah, this one is bounded width, I think. Yeah, also. Yeah.
What is the meaning of bounded?
So bounded width is exactly this. I showed this width. So bounded width will simply mean that you argue about joint. So a k comma L bounded width algorithm will do the following. It will take every k tuple of variables. It will argue about their joint possible assignments by looking at any L tuple of variables and all the constraints in it. So it's essentially just you locally infer what you can. Now the extent to which you cast your local net is captured by these parameters.
Okay.
And they have this collapse theorems that 2, 3 is as powerful as any k and L. And really 2-sat type thing will be like a 2-3 algorithm, because you will say that x implies y and y implies z, so you can infer x implies z. That's the extent of inference you do. That's enough to solve 2 SAT. And so bounded width is, yeah, there is some subtle reason this is not exactly width 1, but somehow this is still constant width, I think, this algorithm. The LP based thing is constant width. Yeah, there was some false claim that this LP works if and only if you have totally symmetric thing, but I think that's, I think width 1 is even simpler than, maybe this is width 2 or something. Yeah, and there are also these connections to these Sherali-Adams, these hierarchies of LPs. Yeah. So for example, 2 SAT will not be solved by this LP, but it will be solved by LPs if you have consistency on marginals of pairs. So that will be captured by level 2 Sherali-Adams. That will capture 2 SAT and somehow corresponds to width 2. But if you take linear equations, even like linear number of levels of Sherali-Adams cannot solve it. So these are these results of Grigoriev and Schoenebeck and so on. You can have a linear system which is basically essentially unsatisfiable, like a random system of linear equations, but the LP will think it is satisfiable even if you have consistency not just on marginals on variables, but huge number of variables, like n over 100 variables at a time. So constant width, just think of it as algorithms based on just local inference. So you refine your values based on local inference and you keep going, and if you stabilize without emptying out anything, then you deem yourself as satisfiable, and if that's the correct strategy, then. And the reason it doesn't work with linear equations is that the only contradictions you might get, if you take a random system of linear equations, the only contradiction will involve lots of constraints.
So does constant width imply that you go to some constant level of the Sherali?
I think so, yes.
And do the same thing there?
Yeah, same thing.
The size of the LP will become n to the power k or something.
Yes, yeah,
K
based on the k. Yeah, that's right. Yeah. Yeah, other questions? Right. Next week in another room. So